Thanks, Chairman. My name is Yoshimitsu. I want to talk about the actual moon robot operation and how we use the good radio technology to that kind of operation. What I talk about here, this is the actual moon robot, which is actually on the moon. So this one went to the moon this January, and about the so it's very small. So I can here. Okay, this is good. Actually, this robot boarded on the small moon lander, what is called SWIM. This one actually launched in August last year and landed on the moon surface this January. And this payload consisted of two robots. One is the Levan, which is I am the primary investigator of this Levan payload. Another one is Lev2, which was constructed by the Japanese Space Agency. And Levan itself was not the Japanese Space Agency's payload. This one was developed differently from the project budget, and the academic people in Japan cooperatively worked to develop this project payload. And this actually this spacecraft actually landed on the moon, which is called SWIM. This was not the so large spacecraft. So initial mass is around 700 kilograms, and including the 500 kilograms of the fuel. So compared with another lunar lander, it was very small, but still the landing was successful. And this spacecraft, the purpose of this spacecraft was to land to the moon surface very smartly. What is smart is there are three things about that. The one is the safe and soft landing to the surface. So for doing that, we use the imagery of the surface to avoid the obstacles autonomously. And next one is precise pinpoint landing. So we sought to land to the designated place in 100 meters of the error. So this was also used the imagery of the surface. And of course, the autonomous landing. And so we are very concentrated on this kind of what is called smart landing to this spacecraft, this mass space. So there are not so many masses to make a surface exploration after landed. So, but what that means that actually our payload was installed in this spacecraft, but they almost abandoned to us, and so what means that from them is that so we had an opportunity to install some payload, but everything else has to be done by ourselves. So that's why we use the good radio technology to the actual ground receiving system. So this payload, just before the landing, the two payloads, Lev1 and Lev2, were deployed from this payload. So the bigger one, which had a mass of around 2.1 kilograms, and the second one, which was smaller than Lev1, had a mass of around 250 grams. And actually, this was the actually installed in the spacecraft. This was taken then in the clean room of the launch site. So you can look at the Levan there, but actually this one is an upside down. So the spacecraft itself was mounted upside down to the rocket. So actually this payload was suspended from the spacecraft, and just before so actually this is a process which this robot took. So just before the landing to the surface, the main spacecraft stream ejected two payloads onto the surface. After that, the actual altitude is around 5 meters or so. So the okay, so the Revan payload successfully landed on the surface, and after that, this one moved very, very autonomously, and there was a sort of transmitter inside the robot, and transmitted directly transmit the so obtained data or the to the Earth. So there was no help after the deployment. So actually, this one has so detail of the Revan payload. So you can look at the big wheel, and so you can turn the so direction by rotating the wheel. And there's a hopping part, so at the tail side of the body, and there's a spring, and if you put into the so hopping part into the body, and then the so some kind of latch mechanism was released, and there's a spring, and the coil spring, and coil spring pushes the hopping part up backward, and so kick the surface to hop into the free space, and on the so ground experiment, this one hopped around 1 meter in 0.5 seconds. That means the gravity of the moon is 1/6 of the Earth. The robot hops around 5 or 6 meters in 3 seconds. So that kind of the hopping actions are repeated to move around the surface. So actually, so we have to deny so. Okay, and we had an also independent transmitter on this on this payload. We used the two frequencies for the transmission to the ground. One was an UHF. It was an amateur radio frequencies, and we opened the this kind of reception of the radio to the amateur. So amateur listener. And some of the amateur listeners all over the world listen to the radio from this. And another one is S-band. That's a very, very normal frequency used for their spacecraft. And this was the actual motion on the surface. Okay, it takes only so. So actually after the hopping actions, so we did not know the actual attitude on the moon surface. So we have to recover the attitude again, capable enabling the hopping action again. So we use so there are several cases where the actual attitude on the surface, but in any way we can recover the attitude and then hops again, and this is the repetition. So as long as this repetition went, we could so this robot could explore in as long as the power was provided. And this one is a Lev 2, so this is a very typical two-wheel type robots, and the merit is very, very small, but there's no independent transmitter to the ground, so the generated data are once transmitted to the Lev1 using the Bluetooth, and then the Lev1 store the data of the Lev2 and transmit the data to the ground by using the S-band radio. And so we have to go to the actual transmission. So we use the very, very small communication module installed in the robot. And we use the two frequencies, S-band and UHF. This is actually the specification. So in the S-band, so of course the frequency is around 2.2 gigahertz, and actual radiated power from the module is 1 watt. And so the modulation method is very, very typical for use in the spacecraft. And the actual operation, so we can change the bit rate, but actual operation bit rate is around 1 kilo bps, and The right figure, actually, this is a display of the spectrum analyzer, and you can look at the center at on the main carrier. But there are several sub-carriers, and in the first carrier, you can have data included in the phase modulation. And the UHF transmitter has this kind of module, so this kind of specification. We use the amateur radio frequency, which means that the frequency is around 440 megahertz, and also the radiated power is around 1 watt. And there are several modulation methods. So one is the same one for the we used in the S-band transmitter, but so bit rate was not so fast since the frequency is different. So we only attained to 32 bps, only 2 bps, which is not so fast. So basically, when the image is transmitted, S-band transmitter was used, and the UHF transmitter only used for the when the so the S-band transmitter was not good, or the not so good. So and used for the transmission of the very, very short message, including the Rover status. And we also use the Morse code in the main carrier. So there's an amplitude change in the main carrier, and which the Morse code is included. And this was, we intended to, this kind of the Morse code was listened by the amateur players. And actually, this is the system which we include the Morse code in the main carrier. So you know that the modulation index, which means that the strengths, so the ratio of the main carrier and subcarrier. So for the spacecraft, the main carrier is very stabilized to measure the Doppler shift, and the actual data is included in the subcarrier, which are then the definite distance from the from main carrier, and we change the ratio in the main carrier and subcarrier. So if you have a strong main carrier, you can easily track the main carrier, but the data is not a little bit more difficult to decode. But if you increase the modulation index, and this means that the main carrier strength of the main carrier gets lower, but the subcarrier strength gets higher. And we can change the this kind of the change of the modulation index to include the Morse code. So when the main carrier is higher, that means the modulation index is very normal. So it means that zero. It's in the gap for the Morse code. And if we decrease the main carrier, it means the dash or dot. So this kind of the modulation is included in the main carrier. And for the reason why we did that is that you can listen to the Morse code in your ear if you use the FM transceiver, and so the FM tuned in the main carrier. So we actually debug this kind of the system by listening to the sound using the FM transceiver located at the near side. So this is actually radio we received in one of the tracking antenna in our domestic area in September 2003, just 1 month after the launch. So it was not on the specifics in the trip to the moon, but we this one is the first time we switched on the module. So there's several radio source included, and the main one and the subcarrier also observed. And if you detail this, look at the radio, so you can have this kind of the radio strength, a sequence of radio strengths, and including the message in the Morse code. So we have CQCQDE, and again the cosine of Lebrun, and after that 56 letters, including the status of the Rover, and the end PSKE. This kind of the message repeated when we use the USS transmitter, and the Lebrun status was included in the 56 letters. And if you have this kind of letters, we can have an status of the Rover. And we so actual tracking antennas, like we could not use the decoding system of the Japanese Space Agency, but so that's why we collected as many antennas as possible. And of course, we used the 2 antennas from the Japanese Space Agency, but also as well as the university antennas. And the 2 antennas from the Japanese Space Agencies are used for the S-band tracking, but another one from university was used for the S-band, and the last one used for the UHF tracking. And outside of the our country, the mainly antennas in the European area are used, and we have an cooperated work with the DSN, NASA, and the antenna from Madrid are also available. And this was the volunteer people from Netherlands. 3 diameter of the 25 meter also used to track the receive the radio from the about the UHF radio from the moon. And the usage of the antennas are like that. Japanese 2 antennas are located in domestic area, tracked the main spacecraft stream, but they did not decode the radio from us. So we had an independent ground system. So since the stream and the Lebrun are almost the same, are located almost the same place, and the antennas are pointed, but there's no decoding on the ground. So we just had an ground system, and which included the good radio technologies, and the NASA DSN. So of course we had a cooperative work with NASA, and they tracked the stream spacecraft, but they had a capability of the the demodulation of the maximum 4 spacecraft in 1 antenna. So they can't decode our radio also. The both spacecraft stream and Lebrun use the S-band, so it was not so difficult for them to get the actual packet from the radio. And the another university antenna in Japan, so Fukui was used for the S-band also tracking, and we put the decoding system used to where the GNU radio technology is used installed in that antenna, and they had a real-time decoding for using that. And the USS receptions are like this, and we had another one domestic antenna which is dedicated to USS reception. We use of course, and so we constructed the independent decoding system also for this university, and real-time decoding was also made. And so voluntary people from European Ringero in Netherlands antennas were also used, and they stored the data, saved the data, radio waves in their website, and we use the their data to decode the packet after that. And of course, the USGS radio was open to the general people, and some of the people in Japan, amateur people in Japan, tried to receive the radio, but totally we had not good news from them. And this is actually the recording system constructed in our antenna. So our policy is to so there was only one chance. So we expected that so radio durations were not so long. So we want to concentrate it on the radio recording for the so big parabolic antennas. So in the domestic so Japanese Space Agency antennas, we install the radio recording system only, and after that we put the recorded data back to our campus and replay the radio, and the actual packet extraction was in our laboratory after several days of the landing days. So actual decoding scheme was like that. So in our as long as the S band in our domestic antenna, so the radio recorded files are obtained, and these files are brought back to the our campus, and we use the several demodulation or decoding system to get the frame data, and in our DSN of Fukuoka University, they had a real-time recording, so there was some frame data already generated at their site. And both frame data are combined and use the PC software to get the actual telemetry data, and which included the status of Rev 1 as well as the images taken by the Rev 2 Rev 2 system. So this is actually the decoding the process machines. So of course, we had a small communication module, and they provided also the decoder of their products, but the SN was not so good. So we used this kind of decoder for the debugging or the development phase, but it was not used to the actual operation since the signal was not so high. And we bought very, very expensive products from Europe, and which was very, very powerful, and the decoding was very good, but still the expensive. And the third one candidate is a good radio software, and we constructed the actual sequence to decode the frame data back from the recorded radio. And the actual result was that this image was the actual landing status of the stream. So the attitude the spacecraft was upside down, unfortunately, but still the landing was successful. And this one was transmitted to our payload from the Rover payload and recorded in our laboratory. And so the actual result was that landing was successful since the radio from the spacecraft was reached after the landing. So there was no crash landing. And about the precise landing, the actual error from the designated place is 55 meters, and which is less than 100 meters, and so we also attained the pinpoint landing also. But the attitude was not perfect. So, and after that, this one survived for a few months around for the experience several nights. And Rev 1 result was like that. So so we had a radio from the after the deployment, and all the station received the radio, sometimes S-band, sometimes UHF. And but the landing timing was not so good for the in our domestic area. Since the so landing time is almost the moonset in our country. So the loss of the signal was very, very soon after the landing. So the in our so most in our antenna located in the most west of our country, of our land, received around 80 minutes after the landing. But after that, we lost the moon in the sky. So the European antennas are very active to look at the moon. So there are several data coming from the European side. And after that, and we also collected the status data from Lebanon. So that, and according to that radio, so the status data, we had 7 hopping actions are made on in around 2 hours after the deployment. And so the robot was very, very good in terms of the mobile system as well as the so radio from the moon. Oh, not so. Okay, summary. This was a summary. It's almost the same at the end. So since the Lebanon payload was an optional payload, so we are abandoned from the mainstream of the space exploration in our country. So we had to develop our independent ground system and of something. And so we also installed a very small communication module capable of the direct transmission to the ground. And the Lebanon worked very well. And we used amateur radio frequencies, and that means and then Lebanon became the first amateur radio station on the moon. So that was recorded in the Guinness books. And American people actually so registered this kind of the so this kind of things to the Guinness World Record. And so we are not so confident about the actual reception system using the GNU radio. But we are not confident about that. And since we are not now in our mainstream the space exploration, we are also running short of the budget, and basically we use the traditional company to make the ground system to construct the ground system, but we had not so much abundant budget now, so we want to replace this kind of the old traditional type system to the another new one, which include the GNU radio. So there are several acknowledgement of this kind. So we basically to the European people. And yeah, that's it. Thank you.